Asthma affects more than 25 million people in the United States alone. And even after decades of inhalers and steroid treatments, most therapies still focus on treating symptoms after an attack has already occurred. What fascinated me was discovering that many asthma patients have low levels of a molecule called interferon gamma, which helps regulate the immune system and prevent excessive inflammation in the airways. So I started wondering, what if we could deliver quick genetic instructions directly into airway cells to boost interferon gamma production before an asthma attack even started? This question led me to nanotech, mucus physics, and eventually to building my own 2D nanoparticle drug delivery simulator in Python. The idea behind the nanoparticle was very simple. I designed it using three main components. First, a chitosan core. Chitosan is a biodegradable polymer derived from crustacean cells. It naturally sticks to mucus and is commonly researched for gene delivery. Second, a PEG coating, a slippery outside layer that helps nanoparticle move through thick airway mucus while also slowly releasing drugs over time. And finally, the DNA or RNA payload itself, the genetic instructions that potentially encourage airway cells to produce more interferon gamma. Together, these components form a nanoparticle about 100 nanometers wide, designed to survive the mucus barrier, reach airway tissue, and gradually release its therapeutic payload. But designing the nanoparticle was only half the challenge. I also wanted to understand how thousands of these particles would actually behave inside the lungs. So I built a simulation. Using Python, NumPy, and Matplotlib, I created a 2D animated model of the airway environment. The simulation divides the airway into three layers: mucus, tissue, and of course, air. Each nanoparticle starts in the air layer and moves through the system using Brownian motion, which simulates the random molecular collisions particles experience in mucus. To make the model more realistic, every nanoparticle was assigned a slightly different degradation and release rates. That way, particles release their payload gradually instead of all at once. As the simulation runs, the particles change color based on how much drug remains inside them, allowing me to visualize diffusion, degradation, and drug delivery in real time. One of the most interesting parts of this project was realizing how interconnected biology, chemistry, physics, and computation really are. Small design changes like adjusting the PEG thickness or degradation rate completely changed how effectively the particles reach the tissue. More than anything, this project taught me how to think like a scientist, breaking down complex systems, testing assumptions, iterating on models, and using code as a tool to make invisible biological processes visible. And while the simulation is only a simplified model, it opened the door to future improvements, like adding immune cell interactions, mucus flow dynamics, or even full-on 3D modeling. This project started with a single question about asthma, but became something much bigger, an exploration of how engineering and computation can help us better understand and potentially improve human health.